Hi, welcome all. In this video, we shall be discussing about the simulation of freely falling object. We will use Euler's method. Okay, the steps we have already explained in another video. We'll just see the steps involved. You must have all the initial values. T equal to 0, y is equal to h, and v is equal to 0. These are the iterating steps. Y is equal to y plus h into f1, where f1 is v and f2 is minus 9.8. So we have to iterate these three equations, namely y is equal to y plus h into f1 of this thing, v equal to v plus h into f2, and t equal to t plus h. Okay, so let us consider the algorithm. Okay, so we have to define f1 of t comma y comma v, okay, as what is f1 of t? It is just v, and we have to define f2 of t comma y comma v, which is nothing but minus 9.8. Now we need to initialize everything. Initial conditions. So what are the initial conditions? When t is equal to 0, here y is equal to some h, you may choose some numerical value for that, and v is also 0. So you may read that or initialize. You may read from keyboard, okay, or you may initialize this. Now what is the next step? You need to initialize everything. Now you need to calculate the time step, okay, or you may choose some time step that is h is equal to some, that is again some initialization. So h is equal to some 0.01 second, because for Euler's method you know that h must be really small. So after that you must iterately calculate these things. You must calculate new value of y as y plus previous value of y plus h into f1 of t comma y comma v, and then you have to calculate the new velocity as previous value of velocity plus h into f2 of t comma y comma v, and you have to calculate t is equal to t plus h, and you may print, if you wish you may print or plot these results. Okay, so that depends. In order to see this, better we plot these results, and in order to plot that you must have some sequences of time, sequence corresponding velocities, and sequence of corresponding positions. So you must initialize some capital Y to store this as store y position with the initial value of y, and in order to store the velocity you may have some lists like this, well, and you may have some position, velocity, and time. To store the time you may have some list called time, and you may initialize that with the t. Okay, this is to plot the things. So in order to plot you must repeatedly calculate the new position and new velocities until it reaches the ground. So what happens when the body reaches the ground level, its y coordinate becomes 0. So if y coordinate is greater than 0, that means positive, you must iterate, you must find the new position. So we'll use while loop to stop this simulation. So while your y is greater than 0, that means positive, you must do all these steps iteratively, and once you calculate the new values of position, velocity, and time, you must append those things into this list. So you must append t, y and v to time, comma, or you may call this as position, that is more readable, comma, pos, comma, velocities respectively. So after this loop you may plot time versus position graph, as well as you may plot time versus velocity graph. Okay, so this is the algorithm. So basically we have to do all these steps. So you can see how we have proceeded. Okay, what we have done is we solved two equations simultaneously, equation 1 and equation 2. Okay, now how you solved? Just like we have solved a single first order differential equation. We initialized everything, we repeatedly calculate the new dependent variable and new independent variable. But here we have two dependent variable, namely position and velocity. Okay, there in the case of the previous example there will be only one independent variable and one dependent variable. Here there will be one independent variable and two dependent variables. That's only difference. So to begin with, you must have all the initial values for all the three variables, independent variable and both the dependent variables. Okay, so this is the only difference. Hope you understood. Now one important remark. See, our functions are really small, no? Our functions are really small. That means first function is just v, it's not a complicated function, and our second function is minus 9.8, that's a constant. So you may just use another code, something like this. You can skip these two defining steps, and then instead of writing y is equal to y plus h into f1, you can just write f star h star v, and instead of calculating the new velocity as v plus h into f2, you can just call it as v plus h into f2 here is minus 9.8. so it doesn't matter. Okay, it doesn't matter how you write this, but I strongly recommend this thing, because for any problem you may switch this algorithm, because for different differential equations these functions f1 and f2 may be different and the initial conditions are different, however the algorithm remain the same. So this will increase the readability. The first algorithm increase the readability, this will also do the thing, but still I strongly recommend the first one, that makes a general algorithm for the for almost all the forthcoming simulations. Okay, now let us see the code. Okay, let us translate that into Python code. So for that, let me take a new file. Okay, so let me import matplotlib .pyplot as plt, because we need to see both the graphs. Okay, now I have to define two functions. Define f1 of t comma y comma v, and this is nothing but our function f1 is nothing but v, so we'll just write return v. So actually we doesn't recur this thing, but this will really help us to modify our program for any simulation. Now we'll define the second function. Define some f2 of t comma y comma v, and there it's really simple, you just return minus 9.8. okay, you will you may at this time feel that the second algorithm may be more convenient, but later when we modify this program, this point will be very clear. For instance, if you consider the fall through a viscous medium, you can very easily modify this program. So we'll see that in the next video. For the time being, you just follow this algorithm. That will be more useful. Now the next steps is to initialize everything. So we initialize t equal to 0, then we initialize the initial position y is equal to some h in general, but we'll choose some 5 meters. You may ask the user to input this data, but I just choose some 10. So this is my y. Now the next step is I have to initialize the velocity, that will be 0. Now I have to choose some time step, say 0.01, and then I have to store all the time, position and velocities, and for that let me call time, let me create some list, time equal to t, so it's at beginning value, and then I have to get the position, so POS equal to then the y coordinate. Then the next step is about velocity, so velocity is equal to its initial value of v. Okay, that's it. So I have already constructed some containers to store all this information, and then I have to start the loop while the condition is this, while my y is greater than 0, that means it hasn't touched the ground, I have to find the new position. So how I proceed? I proceed like this: y is equal to previous value of y plus h star, because dy by dt is v, so please remember it is the first equation. So when you solve the first equation, you will get the new y position, f1 of t comma y comma v. Then we calculate the new velocity, v is equal to previous value of v plus h star f2 of t comma y comma v. Okay, and I can calculate the new time as t plus h. So once I have calculated the new position and velocities at the new time, you have to store this information in the container, namely time, position and velocity. So for that we append this information, time dot append t. Your program may looks lengthy, but please remember the algorithm and translate that. Okay, time dot append. Then next step is position dot append. We have to append the new position, that is y. Then we have to append the velocity, so velocity vel dot append v. So everything is fine. So once the loop is over, you just need to plot it. So we'll plot as two figures. We'll have figure 1 plt dot figure 1, and let me give the title as plt dot title position time graph, position time graph. Okay, and I have to plot this information, plot time comma position, it's POS. Okay, oh sorry. Okay, so this is figure 1. Next I have to plot the second figure. Okay, plot figure 2. The second figure is velocity time graph. So there I have to plot time versus velocity, and both the figures are ready. Now I have to show this plt dot show. Oh, here I made a mistake. plt dot plot. Okay, the next step is to save this. So I'm gonna save this. Save. I'm going to save that in, okay. It is freely falling. It's free fall. So let me call it as free fall. Okay, save. Then let me run the code. Oh, sorry. There's a mistake. So I have to close the inverted comma. Okay. Then let me run the code. Okay, I made some more mistake in line 22. So here it's not plot, it's plt dot plot. So that's a mistake. So we have solved that. Okay, the code is ready and the result is ready to see. So this is a position time graph. Hope everyone remember how the position time graph of a freely falling object is. Okay, this is position time graph. So it starts from 10 and it falls up to 0 in 1.4 seconds. Okay, roughly. And this is the velocity time graph. You know that it is a uniformly accelerated motion, so its velocity time graph will be a straight line, inclined like this. Its slope is negative because our acceleration is negative. So velocity keeps on increasing its magnitude in the negative direction. So at 1.4 second it reaches the maximum, that is -14 roughly. Okay. Now I wish to make one simple modification. I wish to know what is the time of fall. So for that I can print the result. So the last t value will contain that information. So I'm going to print time of fall. Print time of fall equals comma t. The last t value will indicate the time of fall. So we shall see the result. Okay, it takes 1.44 seconds to fall. Okay, and you may check the result. So you know the formula to fall a particular height. Okay, so you may modify the program something like this. If you wish to get this value from the keyboard, you may give some input function, input the height from which it falls. Okay, something like that. Hope you understood. Okay, now let us consider some modification. If it falls through some viscous medium, what will be the case? So actually I will give you the modification. It's an assignment for you. So it's an assignment. So try fall through viscous medium. So I shall give you the simple differential equation. So in the previous case of free fall, the only acceleration is -9.8. Okay, so we choose this as the y direction. Okay, we choose this as the y direction. This is the direction of fall. Now we will consider an object like this. So this is our object. It's moving downward through some viscous medium with some velocity v. So what happens is it experiences a force, gravitational force mg, as well as it experiences an upward force called viscous force. And this viscous force is proportional to its velocity and is in the opposite direction of velocity. Therefore, its accelerations are, one acceleration is in the downward direction, that is g, that is negative 9.8, and there will be one more acceleration, some constant into velocity in the upward direction. Therefore, such an equation can be written as, so this is the case of free fall. So here there will be an additional term. What will be that term? There will be some other term like kV. The k is a constant. It depends on the medium. For instance, if it is a sphere, then we know that the force is given by 6 pi eta AV, where eta is the coefficient of viscosity, A is the radius, or you might have 6 pi eta RV. R is the radius of the sphere and eta is the coefficient of viscosity. Then all these things are constant. Therefore, I can write the force is equal to minus some constant into V. Therefore, acceleration is also some constant into V. Okay. So this is the idea. So as we have done previously, we have to split this into two first order differential equation. So this equation can be written as d square y by dt square is equal to minus 9.8 minus some constant into v. Okay, so previously this term was not there. Now, as we have done earlier, we write dy by dt is equal to v as the first equation, and with that substitution dv by dt become equal to minus 9.8 minus kV. So previously our F1 was just V, now also it is V, but F2 has changed. Before it was just minus 9.8, but now it is minus kV. So in order to simulate, what you have to do is, in the definition of the second function, you have to add this information. So previously it was minus 9.8, now it is minus 9.8 minus kV, and you have to initialize some k value. Okay, so you need to initialize. So this is the only step you have to do. Okay, so that will convert your chord into fall through viscous medium. So you please try. So we will be discussing that, of course, but you must try by yourself. So we must see how it attains some terminal speed and all. Okay. So this we have simulated freely falling object, and we have just explained the modification required to convert that into a falling object through viscous medium. So I request you to write code of your own. You must practice this. This is really important. Okay. So thank you. We'll discuss that freely falling fall through viscous medium in detail in the next video. Thank you.